All right. Good afternoon, class. I hope you're doing well. I'm kind of eating my lunch right now, so I hope you can excuse me if I eat some. Those are good beans. All right. So today we're officially done with atomic physics, nuclear physics, particle physics, and we are moving on to to our last unit, which is called energy production and climate change. So we're going to start off this week by talking about energy production. Okay. And in particular, we're going to focus on non-renewable resources. And so what a non-renewable resource is it's basically a source of energy for which the rate at which we use it is greater than the rate it is replenished. So, hey, Ben. So, for example, oil. Oil is being renewed. There are animals dying in bogs, and they're decomposing and turning into oil as we speak. It's a very long process, but it's a very slow process. The rate at which we're consuming oil is much greater than the rate at which it's produced. So that means that eventually we're going to run out. Okay. So we're going to talk about some properties of fuels, properties of non-renewable fuels. So and energy density is defined as the heat released when the fuel is consumed divided by the volume of fuel consumed. So it's energy per volume. Energy per volume is energy density. So that means that the units of energy density, I can't remember off the top of my head what symbol IB uses for energy density. So I'm just going to call it and then the units of energy density would be joules per cubic meter. So different fuels have different energy densities. Um, and so this is one of the things that would allow you to choose the fuel that you want to use. If you are in a situation where you don't have a lot of space, then you would want to choose a fuel with a high energy density to as a source of fuel. So this is one of the properties of fuel. Another property of the fuel is called specific energy, which I believe that IB denotes E sub S. And it is defined as heat released divided by mass of fuel consumed. So that would be energy per mass. In particular, this means that the units of specific energy are joules per kilogram. Okay. So what would be situations where you might choose your fuel based on its specific energy? That would be any situation where, for example, on an airplane, it's really important that the airplane is light, otherwise it can't fly. So you would want to use a fuel with a very high specific energy. Okay. Both of these quantities you would look up on the internet. Okay. So for today's daily item, I believe that I have a link to a website that lists several specific energies. So you just look it up. In particular, here's kind of an interesting thing. If you take the energy density and you divide it by the specific energy, you would have energy per volume divided by energy per mass, which is equal to mass per volume, which is density, just regular density. So the ratio of the two is related to the density of the material. So that's something you should know. Another thing you should know is that the energy density and specific energy don't factor in the efficiency of the burning process. So for example, this is purely the heat released. There's going to be some kind of an engine, a heat engine that turns that heat into work, and it's not going to be 100% efficient. And so the efficiency depends on the method. So, and just to remind you, the efficiency is denoted by epsilon. So let's do an example to see how this works. A car burns gasoline. With efficiency of 20%. That's that's pretty close to the real efficiency of a car. It's around 20%. All right. And so my question is, how much work can a car engine do? All right. So first of all, let's look up for gasoline. What is its energy density? All right. So I'm going to look this up. I have a web tab open. The energy density of gasoline is equal to oops, I didn't have the right web page. Gosh darn it. Energy density of gasoline. Sorry about this. I'm trying to find the right table online. Okay, here we go. Here we go. The energy density of gasoline is 35,000 megajoules per cubic meter. Okay, so mega means millions. So that's 10 to the 6th. So this would be 3.5 times 10 to the 10th joules per cubic meter. All right. Now let's think about it. What is the volume of a gas tank? The volume of a gas tank, well, it depends on the type of car you have. So I'm going to use my car, which is a Prius C, and it has a gas tank that's 10 gallons. Okay. That's not in cubic meters. So 10 gallons to cubic meters, I'm typing into Google, and it's 0.038 cubic meters. So what that means, so basically the heat that we'll get is going to be equal to the energy per volume. The energy per volume times the volume. Okay. The energy per volume is the energy density of gasoline. So that's 3.5 times 10 to the 10th. And then the volume of the gas tank is 0.038 cubic meters. So working that out, that gives me 1.33 times 10 to the 9th joules of heat are released. Okay. So there you have it. But again, this is just the heat released by burning all of the gasoline in the gas tank. I have to factor in the efficiency of the vehicle. So the actual work done would be the efficiency times the heat released. So it's going to be 20% of that, 0.2 times 1.33 times 10 to the ninth. And so that would be 2.7 times 10 to the eighth joules. That's how much work the car could do. So, if the car was going up a mountain, you could calculate how tall of the mountain could it climb by setting that equal to the gravitational potential energy of the car, something like that. All right. I think we'll do one more example. Let's say a heat engine is 15% efficient. All right. What mass of, let's say, coal is needed to do 1 megajoule of work? All right. So I want to know what mass of fuel. So for that, I would need to know what is the specific energy, E sub S. So I'm going to look up the specific energy of coal. And now I'm on the right web page. So I know that the specific energy of coal is specific energy of coal is 22.7. So we'll say 2.3 times 10 to the 7th joules per kilogram. That's the specific energy of coal. Okay. Now I want to do 1 megajoule of work. So how much heat needs to be released? Well, I have 1 megajoule, 1 times 10 to the 6th, is equal to the efficiency, which is 15%, times the heat released. All right. So the heat that I need to release is going to be 6.7 times 10 to the 6th joules. You be quiet, Bug. Knock it off. He's barking at kids. So that's the heat that needs to be released. So what I'll do is the heat that needs to be released is equal to the heat per mass times the mass. So the heat that needs to be released is 6.7 times 10 to the 6th. The heat per mass, that's the specific energy, which is 2.3 times 10 to the 7th times the mass. And I can solve for the mass. And I get M equals 0.29 kilograms, which you could then convert, if you wanted to, into the cost of that fuel. That's the other cool thing about this. You could convert it to cost. All right. So these are some things you want to think about if you were you know, an engineer that, and you're choosing what fuel you're going to use. Um, you want to know what is the specific energy, what is the energy density. All right, that's all I have for today. I hope you enjoyed this lesson, and I will talk to you tomorrow with more discussion of energy production. Bye now.